All right, so we're going to continue our discussion on lenses and mirrors, ray optics. Last time I left you with this problem. We have an object placed in front of a concave mirror or a converging mirror, and we place the object closer to the mirror than the focal point. And so I want to do the ray tracing for this particular situation and see where the image is located and what kind of image it'll be. So I'll start. Let's take our first ray. As usual, it goes parallel to the principal axis to the mirror, and then when it reflects down through the focal point. So there's our first line. The other line I can draw, I can't go through the focal point because I'm already past it, so I have to do the third line, which is the one that goes through to the center of the mirror and then reflects back at the same angle. So here's this, and back at the same angle again, and there's that line. And so this is the ray tracing. Now we have an interesting situation here, similar to when I had the convex mirror. These two light rays diverge. They don't converge, they don't come together and cross, which is what's necessary to have an image formed. But, as with the diverging mirror, I could do a little trick, and that trick is to send these light rays backwards, virtual light rays, fake ones, the little dotted ones, and then we can see what happens with them from there. So there's the red one, and then the yellow one, we send him back as well. And indeed, we find that these two rays do converge. However, they converge on the opposite side of the mirror. And where they converge, right there, that's where my image is located. So, this gives us a virtual image. Obviously, it's virtual because where the image is formed is on the wrong side of the mirror. This right side is past the mirror, and of course light can't go through a mirror, so there's no real light over there. However, the light rays act as if an image is formed on this side of the mirror, and we call it a virtual image. What else do we know about it? Well, the arrow is pointing up, so this is an upright image. It's not inverted. And I could look at the size of the image arrow, compare it to the size of the object, and the image is bigger, so it's magnified. And so here we have an important thing to note, which is even though we may call a concave mirror converging, that doesn't mean the light rays always converge. Here is a big thing to remember. Every time an object is placed within the focal length of a mirror or lens, as we will see in the future, you always get a virtual image. So, we know of two types of mirrors: convex mirrors, which are called diverging mirrors, and I know those mirrors we always have virtual images. Those are the mirrors that look like this. That's the kind of bulges outwards. That will always give us a virtual image. Then we have these converging mirrors, which are the concave ones. And for those types of mirrors, sometimes you get real images. Those times are when the object is past the focal length, further away. But we can also get virtual images with them as well, and that's any time we put the object inside the focal length. Now obviously one can ask the question, okay, well if after the focal length it's a real image, inside of the focal length it's a virtual image, what happens when I put the object on the focal point itself? That's something you should try, but what I will say is, if you do this accurately, which you should try, you're going to find that the light rays go parallel to themselves. If the light rays reflect parallel, then even when you try to send them backwards through the mirror with those virtual lines, they will remain parallel. And so, if you put your object on the focal point, you will always get no image whatsoever. No image will ever be formed. Now, sometimes textbooks will say the image is formed at infinity. All it means is you never get an image. If it's inside the focal length, you get a virtual one. Outside the focal length, you get a real image. On the focal point itself, no image whatsoever. All right, so now what I want to do is let's look at the analytical method. For calculating image distance and is this upright and all of this kind of stuff. Well, in order to do this, first let's see what kind of a question would we be asked. Something like this. An object is placed 20 centimeters from a concave mirror whose focal length is, let's say, 5 centimeters. Calculate the image distance and give the 3 characteristics of this image. And of course, what I mean by that last part, the 3 characteristics of the image, I mean, is it upright or inverted? Is it real or virtual? And is it magnified or minimized? All right, well, this is our problem. So what does the picture look like if I were to draw this out? So we have our principal axis, concave mirror. So here's the mirror. We have a focal length of 5 centimeters. So let's say this is 5 centimeters here. And our object is placed 20 centimeters. So it's basically 4 times further away. So 1, 2, 3. So about right here. Let's say that's our object. So this is the system, and I want to calculate where will the image be for this particular system. Now, first I'm going to solve this analytically, get the answers by math, and then I'll do it using ray tracing as we did before, and we see if they match. So, how do I solve a problem like this? Well, the first thing is the equation we're going to use, called the imaging equation, says 1 over the focal length of your mirror is equal to 1 over the object distance plus 1 over the image distance. So that's going to be the equation we're going to use. There's a second equation we're going to need, which I'll go ahead and write now, and that's the magnification. In a magnification, there's kind of 2 forms. The first form says a magnification is equal to minus the image distance divided by the object distance But there's a second way, and the second way is the image height over the object height. Now that just means, the image is 10 centimeters tall, the object is 5 centimeters tall, so that means the image is twice as big as the object, so the magnification is 2. 10 over 5 is 2. So image height, object height, that means the size of the image and the size of the object. Image distance and object distance, that means the distance from the object to the mirror is called the object distance, and the distance from the image to the mirror is called the image distance. So with these two equations, we can get all the information we need about our particular problem. So let's get the information from our problem again. Our problem said we have an object that's placed 20 centimeters from a concave mirror. So we know object distance is 20. Now, I will say right here, yes, this is physics. We should be using meters as our units instead of centimeters. But if all of the distances we use in our problem are centimeters, then everything can be in centimeters and we'll be okay. Once you start mixing meters and centimeters, then you better convert everything to meters. And also, when you give an answer, you better be specific about if you're talking about centimeters or if you're talking about meters. But for now, I'll go ahead and use centimeters because there's no big deal in doing that for these problems. All right, what else? So 20 centimeters away, the focal length of the concave mirror is 5 centimeters. So focal length is 5 centimeters. Now here's another thing. This is very important as well. The focal length can be positive or negative. Now, how do I know if the focal length is a positive or a negative? It's purely arbitrary. It was a standard that was chosen in the past, and the standard goes like this. If you have a concave mirror, then it's positive. If you have a convex mirror, then it's negative. Okay? That's a standard that was chosen in the past, and we just stick with it. So here we're told this is a concave mirror whose focal length is 5. So F for our problem is going to be positive 5. If this were a convex mirror, obviously it would be negative 5. All right, now what is it I'm looking for? I want to know what is the image distance. And I also want to know about the different characteristics. Is it magnified or whatnot? So, here's our information. Our equations are given. Let's go ahead and solve it. 1 over F is 1 over dO plus 1 over dI. Plug our numbers in. 1 over 5 is 1 over 20 plus 1 over dI. I want to solve this for dI, so I have 1 over 5 minus 1 over 20 is 1 over dI. And then 1 over 5 minus 1 over 20 turns out to be 3 over 20. But I don't want 1 over dI, I want dI itself. So I have to flip this answer. And when I flip it, I get the image distance, dI, is 20 over 3 centimeters. Now, of course, I could convert this to a decimal. That's no big deal. Or you could leave it as the fraction. Either way is fine. The decimal, of course, would be 6.67 centimeters, I believe. So there we go. Image distance is found. I now know the image distance is about 7 centimeters, a little bit less than 7 centimeters. Now, what about our characteristics? How do I do this? Well, the first thing to note is a real image is an image whose image distance is positive. So if you're doing this calculation, you calculate your image distance. If it's a positive number, then it's a real image. If your image distance turns out to be negative, it's a virtual image. So, for our problem, we got a positive image distance. So, for right now, I know this is real. What about the other two? What about upright and inverted and magnified and minimized? Well, the rule says when you calculate magnification, if the magnification, the number itself, so don't worry about, well, let's do it this way. When you calculate the magnification, if the magnification is positive, then it's an upright image. And if the magnification is negative, it's inverted. And then the last thing we're going to have to know is if the number itself for the magnification. So you take the absolute value of m, whatever that happens to be. If that absolute value of the magnification is greater than 1, it's called magnified. And if the absolute value of the magnification is less than 1, so it's a decimal number, then it's minimized. So, now we need to calculate the magnification for this to try to get these last two pieces of information. What do we know so far? Well, we still have DO was 20, F was 5. We just found DI is 20 over 3. So now we want to find magnification. And if you remember the equation for magnification, magnification is minus DI over DO. So, minus 20 over 3 divided by DO is 20. Stick this in your calculator or do the little math. This turns out to be minus 1/3. So that's the magnification. And I look at this magnification and it says, first of all, it's a negative number, so it's inverted. Then I look at the number itself, forgetting about positive or negative. 1/3 is a number less than 1. Number less than 1 means it's minimized. It's smaller than the original object. So, our final answer. What's our final answer for this problem? Well, first of all, we wanted to know what's the image distance. DI is 20 over 3 centimeters. Then we wanted to know three characteristics. Well, image distance of 20 over 3 was a positive number, so I know this is a real image. I then calculated the magnification. I got negative 1/3. The fact that it was negative tells me it's inverted. And the number itself of 1/3 tells me this is a smaller image, so it's minimized. So that'll be my answer. Now, what I want to do, of course, is I want to try to do this by ray tracing and see if the picture way of doing things matches the mathematics. So let's redraw the picture. Here's my concave mirror. I was told the focal point was 5 centimeters. And then my object was at 20, so here's 1 times, 2 times, 3 times, 4 times. So here's about 20 centimeters away. And so now let's do our little ray tracing tricks. So the first line parallel to the principal axis all the way to the mirror. Once it hits the mirror, it then travels through the focal point. Another line we can do was the line that goes from the object through the focal point to the mirror. So, like that. And then when it reflects back parallel to the principal axis. And then I don't need to worry about a third line. I can draw the third line if I want, but as long as I do 2, I'm fine. Where these two lines cross, that's my image. So there's my image. Now, does my picture match my analytical method? Well, first of all, the analytical method says my image should be 20 over 3 centimeters away. Well, 20 over 3 is 6.7 centimeters, about. So this says the image should be a little bit further than the focal length, because if you remember, the focal length was 5. Well, let's look. The green dot, that's my focal point. That's 5 centimeters, and my arrow is a little bit past it. All right, so that matches. Another thing, is this a real image? Well, if you remember the rule for mirrors, if the image is on the same side of the mirror as the object, then it's a real image. Here in our picture, the arrow and the object are both on the left side of the mirror, thus it's a real image. So that matches. Inverted. Analytically, we're told it's inverted because our magnification was negative. Look at the picture. The image arrow, the gray one, is upside down. That means it's an inverted image, so that matches as well. And then finally, analytically, we're told this is a minimized image because the absolute value of our magnification was 1/3, and 1/3 is a number less than 1. Looking at our picture, is the gray arrow smaller than the black arrow? Yeah, so our image is indeed smaller, so everything matches up. And that's the good thing, because in general, you're a lot more accurate with mathematics than you're going to be with pictures, especially if you're not using rulers and everything to try to be as perfect as possible. And the math part is easier to do than the drawing part, and it's a lot more accurate when you need to get real answers for this stuff. But that's how we do things analytically. Let's try one more example. This time we'll do, let's try an object is placed let's say 10 centimeters away from a convex mirror whose focal length is 20 centimeters. Calculate DI and the 3 characteristics. All right, so what do we know? Well, DO is 10. F, we're told the focal length is 20, but this is a convex mirror, so it's actually negative 20. And I want to know DI. So let's start with the imaging equation. 1 over F is 1 over DO plus 1 over DI. So 1 over negative 20 is 1 over 10 plus 1 over DI. Solve this for DI, we get negative 1 over 20 minus 1 over 10. So I just brought the 1 over 10 to the other side, equals 1 over DI. And then minus 1 over 20 minus 1 over 10. Well, of course, to do this, you got to get 1 over 10 common denominator with 20. So 1 over 10 is the same as 2 over 20. So minus 1 over 20 minus 2 over 20 is minus 3 over 20. However, just like before, I'm not interested in 1 over DI. I want DI itself. So DI is minus 20 over 3, which is about minus 6.67. So here's our image distance. Happens to be this 20 over 3 thing again, but that's just because of the numbers I'm using. All right, so we have the image distance. Now, what about the characteristics? Well, first of all, let's go ahead and do the magnification equation and then get all the characteristics at the end. So magnification says minus di over do. Okay, so minus, what was di? Di was negative 20 over 3 over do was 10. Now notice, you have to be very careful with these negatives. There's already a negative in the equation, and di was a negative number. So there's two negatives there. So the negative with the negative becomes positive. So when you do this calculation, you get positive 2/3. All right. Now we have all the information we need. First answer, of course, di, we have that answer. It's negative 6.67. What about the characteristics? Well, the image distance is negative. Since the image distance is negative, I know this is a virtual image. Next, I look at the magnification. The magnification is a positive number, so that means this is upright. Finally, I look at the number of the magnification, forgetting about the signs, whether it's positive or negative doesn't matter, just look at the number. It's 2/3. 2/3 is a number less than 1, so this is minimized. So there we go. There's our answer. Image distance, negative 20 over 3 centimeters. It's a virtual image because of the negative image distance. It's an upright image because of a positive magnification. And the image is smaller than the object because the magnification is less than 1. So as you can see, no matter what system I give you, it's fairly clear how to go about solving these. You're given an object distance, you're given a focal length, solve for the image distance. Once you know that, you can solve for the magnification, and then you get all your answers as long as you know the rules. Of course, we could do other things. For instance, I could ask for where should I put the object in order to get a particular image. Obviously, all you do is you know di, and you have to get do. It's the same thing. It's just you're solving for a different variable. All right, so next time we're going to move on to lenses and see, does the use of lenses to create image change how we do things versus how we do things with mirrors.